Alright guys, welcome back. So we're going to finish up this section and we're going to start with example 8. So we just left off, we were given a polynomial and we were given one zero as well, and we were asked to find the other zeros. Well, because it's cubic, we know it can only really have two other zeros. And so what we did was we verified that -5 was in fact a zero, and then we took this quotient, which is also a factor, and from that factor we found the other two zeros. Okay. Alright, so let's do example 8 now. It says for this polynomial one of the zeros is given, so it's nice that we know one of the zeros without having to do any work. And then it says to find the remaining zeros. Now notice the nature of this zero that's given. It's imaginary, and we know these come in pairs. Okay, so in a sense they're giving us two of the zeros, and since this is a fourth degree polynomial, that really just leaves us to find the other two. Alright, so what you want to do again is first verify that 5i is a zero. Okay, and then we'll go from there. But the first thing I want to point out is that this polynomial is in descending order, but it's got some missing terms in it. Let's see. So if you recall, we need to give those missing terms coefficients of 0 the way I've done here. Okay. Now when I go to write out my row of coefficients to do my synthetic division, I'm going to have some zeros in there. And I first want to verify that 5i is a zero. Alright. Okay, so we're going to run through the same synthetic division algorithm. We're going to drop down to 1. 5i times 1 is 5i. 0 plus 5i is 5i. But here, guys, 5i times 5i is 25i squared. 25i squared. If you remember, I squared is equal to -1. So that's going to make this a -25. Okay. And 19 plus -25 is -9. 5i times -9 will be -45i. Added to 0 will stay -45i. And then again, 5i times -45i will be negative, I think that's 225i squared. But again, I squared is -1, so that'll make the -225 positive. And that's what we're looking for anyway, because we know that 5i is a zero. Okay, so that one checks out. Now, that means that these coefficients right here are the coefficients of another factor, okay, of this polynomial here. So, you know, you could say x minus 5i is a factor. Well, these are the coefficients of a cubic polynomial factor. And so what we can do is to verify that -5i is a zero, because we know these come in pairs. We can go ahead and do synthetic division with this cubic factor that's left over here. Okay, so you just turn around and use those resultant coefficients to perform another round of synthetic division. Okay, alright, so I'll drop down my 1 again. -5i times 1 is -5i. Positive 5i plus -5i is 0. -5i times 0 is going to be 0. Negative 9 plus 0 is negative 9. And then finally, negative 5i times negative 9 is positive 45i. And so we get 0 again, okay? So that confirms that that conjugate is also a 0. And now, guys, these are the coefficients of not a cubic factor, but now of a quadratic factor. And so if we can get this down to a quadratic, we can always extract those last two zeros, if nothing else, by using the quadratic formula. Okay, so I'm going to go ahead and add the x's here. We're not going to have an x term because there's a 0 there, but this is my quadratic factor here. Okay, and so if I carry that over here, x squared minus 9, and we set that equal to 0, you can either use the quadratic formula. Your a would be 1, your b would be 0, and your c would be negative 9. Or you can solve it directly for x to find those last two zeros. And I'm going to solve it directly for x. So I'm going to add 9 to both sides. We get x squared is equal to 9. And then we'll take the square root of both sides, and we'll get x is equal to positive and negative square root of 9, which is 3. Okay, so both positive and negative 3. Those are my last two zeros. When you're working on your homework, they will ask you to list your, how do they say it? Your rational zeros, and then your other zeros. Okay, so your rational zeros here would be 3 and negative 3. The other zeros would be 5i and negative 5i. Okay, so pay attention to that. Sometimes they'll ask you. But in any case, all of my zeros are, and there's 4 of them, 2 of them are real. They're real and they're integers, or rational numbers. And then the other 2 are purely imaginary numbers, or zeros. Okay, so if you were to graph this polynomial, it would only cross the x-axis at these two values, 3 and negative 3. Okay. Alright. Okay, so now we're going to do one more problem like this, in which we're finding all of the zeros of the polynomial. But before we do that, I want to talk about this rational zeros theorem. The reason we're going to discuss this theorem, guys, is because in example 10, it's going to ask us to find the rational zeros and then the other zeros. So this is what I was alluding to earlier. In other words, it wants us to find all of the zeros of this polynomial. But notice, it doesn't give us any with which to start, the way that the two previous examples did. Okay, it's a lot easier when we have a 0 with which to start. My computer froze. Alright. Okay, well, hopefully I'm still recording. It looks like my video froze, but anyway. Yeah, so if we're trying to find all the zeros of a polynomial, we need to be able to start with 1, okay, to get the ball moving, so to speak. And so that's where this rational zeros theorem kind of comes into play. It basically tells us how to find some candidates, and then we can verify or guess and check and verify whether those candidates are actual zeros or not. Okay, so let's look at the theorem. Let's see. Look at the very last sentence right here. If p over q is a 0 of this polynomial right here, then p will be a factor of the constant, so whatever the constant is, and then q will be a factor of a sub n. Well, a sub n is your leading coefficient. Okay, so in other words, p is going to be a factor of your constant, and then q is going to be a factor of your leading coefficient. Okay, and so what this tells us is that if our polynomial has any zeros that are rational numbers, then we can figure out what those candidates are going to be. Okay, and then we can check them. And we do this by finding and listing all the factors of p, and we put all those combinations over the factors of q. Okay, and sometimes there can be quite a few factors, as you'll see in example 9 here. Okay, so p refers to our constant, q refers to our leading coefficient. Okay, so let's look at example 9. It says list all possible rational zeros of the function. Okay, now notice it doesn't say list the rational zeros, it says list all possible. So what we're doing is we're listing some candidates. And so we're going to list all the factors of p, and then we're going to list out all the factors of q, and then we're going to see what combinations those give us. Alright. Okay, so factors of, you can look at this as either positive or negative 35, it doesn't matter. Okay, factors of 35, all the factors of 35 over all the factors of 33. Okay, so what are my factors of 35? Well, 1, 5, remember you're thinking about numbers that'll go into 35 evenly, 7 and 35. But guys, all of these can actually be both positive and negative. Okay, so that's why the sign doesn't matter over here. And then furthermore, factors of 33, well, all these can be positive, either positive or negative as well. So 1, 3 is a factor, 11 is a factor, and then 33 is a factor. Okay, so I've listed all the factors of p and all the factors of q. Or, well, I guess more technically, according to the definition, I've listed all the factors of our constant, and I've listed all the factors of our leading term, or our leading coefficient. And so now it's time for me to actually put these together to construct the possible rational zeros. Okay, so they're going to be fractions. They're going to have this form right here. Alright, so you start with your first one, 1. And I'm going to consider both positive and negative. 1 over. And then you just start putting it over all the factors that you have listed down here in the denominator. So 1 over 1, well, that would just be 1. Okay, so that's the first one. And then 1 over 3, that would be a third, but again, each one can be either positive or negative. 1 over 11, and 1 over 33. Okay, and again, both positive and negative. Then you move on to the next one in the numerator, 5. And you put it over all these factors that are in the denominator, and you repeat that process for all of them in the numerator. And when you're finished, you'll have a list of all the possible rational zeros for this particular polynomial. Now, this is only a third-degree polynomial, so it can only have a maximum of 3 zeros, so obviously not all of these are going to be rational zeros. Alright, so now I'll do for 5. 5 over 1 is just 5. But again, we could have both positive and negative. 5 over 3 is just going to be 5/3. 5 over 11. 5 over 33. Okay? And you just keep going. Now you do 7. Well, 7 over 1 is just 7. Positive or negative, 7 over 3. Kind of running out of room here. Positive and negative, 7 over 11. I'm just going to pick up down here below. Positive and negative, 7 over 33. And then finally, 35 over 1 is 35. 35 over 3. 35 over 11. And finally, 35 over 33, both positive and negative. So if you look at this, this is actually a lot of candidates. Man, it froze again. All right. I've counted these before, guys, and I think that there's 4 on top, there's 4 factors on bottom. 4 times 4 is 16. So there's 16 combinations, but either one can be either positive or negative, so there's actually 32 possible rational zeros. Okay, so this theorem doesn't tell us that this polynomial will have any rational zeros. It just tells us that if it does, they're going to come from this list right here. So knowing this list gives us some candidates with which to start. Okay, and that's what we're going to use when we work on example 10. We're first going to list all of our possible rational zeros, and then from those we're going to check them and see if we can come up with any that are zeros. And that'll help us get this whole sequence started. Okay. Alright, so let's look at example 10. This is the last one. Alright, so here is our polynomial. It's another 4th degree. They don't tell us what any of the zeros are. Okay, so the first thing that I'm going to do is list my possible rational zeros. And remember, a rational number is just a number that can be expressed as a fraction. So all the integers, all the counting numbers, those are rational numbers because they can all be put over 1. Okay, possible rational zeros. Oops. Okay. Well, they're going to come from factors of my constant, which is 21 here. So what are my factors of 21? Well, they can all be positive or negative. 1, 3, 7, and 21. Okay, over. My leading coefficient is an understood 1. It's nice when it works out like this because the only factors of 1 are positive and negative 1. And if you put any of these over positive or negative 1, they're going to pretty much stay the same. Okay, so really our possible rational zeros are just going to be positive and negative 1, positive and negative 3, positive, negative 7, and positive or negative and or 21. Okay, so really I only end up with 8 of them here. Alright, now we need to start checking these. Okay, there's 8 of them. So we're going to check them using synthetic division, because if 1 turns out to be a 0, then what we have left will be a cubic factor. Okay. Alright, so let's go ahead and set up our synthetic division. Our polynomial is in descending order. There are no missing terms, so I can go ahead and write out my row of coefficients. 1, -6, -44, -58, and -21. Okay. Alright, now I need to try one of these. Well, what we can do is we can actually graph this polynomial, and that'll give us an idea of which of these to try instead of just blindly guessing. Okay, so I'm going to go to Desmos. I'm going to graph this polynomial, and I'm going to see if it crosses or touches the x-axis in any of these values. Let me take a peek at this polynomial again. Okay, -6, -44, -58, -21. Okay. Alright, well here it is. This is what it looks like. You can zoom out. It's a 4th degree, so the end behavior, both ends are going up. Okay, but notice it does cross the x-axis in 4 different places, and we know it'll have 4 zeros. Turns out they're all real numbers. None of them are imaginary. But my guess is that this one over here is probably irrational. This one right here is probably irrational, but these two, this one right here at -1 and this one right here at -3, correspond with some of these possible rational zeros. Okay, so I'm going to try, it looks like it's clearly crossing right here at -3, and -3 is one of our possible rational zeros, so that's what I'm going to try first. So see, instead of being given a 0, we're having to use this rational zeros theorem to list a few possibilities, and then we're going to try one. Okay. Alright, so let's run through this. Bring down your 1. We're going to start multiplying and adding. -3 times 1 is -3. -6 and -3 is -9. -3 times -9 is 27. That's going to give us -17. Wait, is that right? Yes. -3 times -17 is +51. -58 plus 51 is -7. -3 times -7 is +21. And so this checks out. This verifies that -3 is a 0, and it's one of your rational zeros. Okay. Now what I want to do, since this was a 4th degree polynomial, these are the coefficients of a 3rd degree factor. So I need to somehow get this down to a quadratic. So I'm going to run another potential 0 through there. I'm going to look back at my graph. It looks like it was also crossing at -1. And -1 is in this list. So I'm going to do another round of synthetic division with -1. And if -1 is a 0, then the resultant factor down here will be quadratic. And that'll allow us to extract those last 2 zeros. Okay. Alright, so I'll drop down the 1. -1 times 1 is -1. -9 and -1 is -10. -1 times -10 is +10. -17 and 10 is -7. And finally, -1 times -7 is positive 7, and we get 0. Okay, so negative 1 is my other rational 0. Now these are the coefficients to a quadratic factor. And so if I take that last factor, set it equal to 0, I can find my last two zeros. Now this one though, guys, I'm looking at it and I can tell that it's not factorable. In fact, I'm going to have to use the quadratic formula. Okay. Oops. Alright, so I'm going to have to come back in here. If you remember, I first showed you this in Module 2. I think it was in week 7, but I put a link to that quadratic solver in Blackboard. I'm looking for it. I'm not finding it. Evidently, it was under week 6, at least for this course. Okay. So in any case, just go back and get that quadratic solver. Here it is, quadratic formula calculator. Okay. So here I've brought it up again, and I'm going to input these coefficients. So remember, A, B, and C. So A is 1, B is negative 10, C is negative 7. Calculate, and look, in fact these last two zeros are irrational because they involve this square root of 2, and they do come in pairs. Remember that? Conjugate pairs. 5 plus and minus 4 square root of 2. Those are my last two zeros. X is equal to 5 plus and minus 4 square root of 2. Okay. Alright, so when I go to list my zeros, I found all 4 of them now. My rational zeros are x equals negative 3 and negative 1. My other zeros, so this could include both your irrational zeros and your imaginary. My other zeros are x equals 5 plus 4 square root of 2 and 5 minus 4 square root of 2. Okay. And then the last thing that we need to do here, it says factor this polynomial into linear factors. Well, we know how to do that. If we know the zeros, we can know the factors, right? We've done that before. So if negative 3, alright, so I'm going to express this in factored form. If negative 3 is a 0, then one of the linear factors will be x plus 3. If negative 1 is a 0, another linear factor will be x plus 1. Okay? Now it gets a little tricky when you run into these irrational zeros because they actually have two pieces. So if 5 plus 4 square root of 2 is a 0, then technically x minus 5 plus 4 square root of 2 is a 0. But notice, when we're subtracting this, it has two parts. So you distribute that negative. So our linear factor will become x minus 5 minus 4 square root of 2. Okay? And then you do the same thing for the last one, x minus that last 0, which is 5 minus 4 square root of 2. See? So when you distribute this negative, you're going to get x minus 5 plus 4 square root of 2. Okay, so you kind of have to be careful here. But this polynomial in factored form would look like this. There's 4 linear factors right here. Okay. So guys, in your homework you're going to have 2 or 3 problems like this. You can list out the possible rational zeros. Sometimes though you can even save yourself some time, just graph the function and you can see it clearly crosses at -3 and -1. Sometimes though, however, what if some of these rational zeros were fractions? Then you might have to know what the actual fractions were before you graph it. Because let's say the function doesn't cross at a nice number, it crosses at a fractional value. Well, to know what value corresponds to that fractional value, you're going to need to know that list of possible rational zeros. And I guess computer's going to freeze for a third time. This is unprecedented. I think it's a software, guys. The college likes for us to use. And it's good software, but it just seems to still have a few bugs in it. Alright, well, in any case, that concludes 8.4. Okay, so we've got a couple sections left for chapter 8 before we're finished. We're going to go to 8.5 next, and we're going to be studying not polynomials but rational functions. So those functions that had restrictions on their domain. Okay. Alright, so I'll see you in that video.